18th training for the technical track for the year. And we have Ken Snyder and Joe on board to team this. And I think I sent an email out with some handouts and such to remote staff. There's some handouts here in the Canaan conference room. And everyone else will just follow along with the folders and such in the different documents that they're going to go through afterwards. If there's anything that anybody has questions on, everything will be on the R drive. And you've got a wonderful couple of resources in Ken and Joe. And as per usual, don't forget to fill out your evaluation and have a wonderful training. Take it away, you guys.
All righty, this is Ken. Thanks everybody for joining us today. It's pretty hard to make earthwork calculations exciting, but maybe we'll make them at least a little bit interesting, and hopefully you will all learn a little something along the way. This is my first Skype training session, so apologies in advance for any technical shortcomings. Joe's an accomplished expert, so I'm depending on him to keep this flowing smoothly, right, Joe?
That's what they say.
Okay, let's go into the learning objectives and we'll go from there. Okay, we're gonna break this up into 3 different sections. The first is talking about best practices for generating earthwork calculations, and I'm going to talk through that. And then Joe's going to talk about the Civil 3D side, about how to build models and build what we need to generate the sections. And then I'm going to close it with a short discussion on what we call recommended practices for earthwork quality control. Keeping in mind that the single biggest problem on a lot of construction projects is utilities, but in my years of experience, earthwork is often a close second, arguments between the engineer and the contractor on earthwork volume. So we're going to look at how to accurately define the earthwork boundaries, apply adjustments to the raw earthwork if necessary, and then make sure we're getting the most accurate picture we can of the project earthwork volumes.
So then after that, I will be showing us how to do 3 different surfaces, one being tin, one being a grid, and the other being average end method to calculate the quantities, and then Ken will discuss the quality control.
Yeah, we have a quality checking process that I think has been shared with you. It's a 1-page summary. We're going to go over kind of the cut and fill and volume reports, share some exhibits that will talk through how we have developed the best practices for actually doing the quality checks of earthwork, and go through some AutoCAD cross sections and how we use that in the checking process. And that's the whole point. Second set of eyes on earthwork. We've had some problems in the past, and as an airport practice, and I'm sure other groups have had too, so we want to kind of demystify the black box of earthwork calculations and make sure everybody's able to open that box up and look inside it and make sure what we're doing is correct. So we're going to start with a very simplistic model of how we generate earthwork volumes. And this is going too fast, Joe. This is cross-section view, but keep in mind we're really talking about generating a 3-dimensional model in Civil 3D. The cross-section view is just to simplify the principles. So the red line, of course, is the survey section. The magenta or cyan line is the subgrade, or the finished grade of the earthwork, if you will. And you can say, we're done. This is, you just let Civil 3D do its stuff, and that's our earthwork volume. But there's a number of things that you really need to be careful when you're generating volumes and building the model, that you accurately are depicting both the subgrade line and the existing ground line to make sure the earthwork is accurate. And let me point out, these are really weird looking sections, but Joe and I kind of modeled this after our Terminal 4 S1 concourse project. We've got taxiways and aprons on each side of that job. It's a hole, and then we're building aprons in the middle, and there's a building right in the center. So it's not a typical roadway or taxiway section like you might be used to using, but it's kind of modeled after a project we're actually working on right now. So you can see the cut sections on the left and right, and the fill sections in the middle. And Joe, you want to move on to the next one? The first thing we need to be careful of is how we're defining the subgrade line for pavement. A lot of times an engineer will tell a designer, go to the typical section and build the model to the bottom of the typical section, the subgrade line. But there are some refinements in that you have to be careful of. What exactly is the bottom of the paving section with respect to earthwork. Sometimes we have cement treated base. An example of that is on the left. That is an imported material, so it doesn't count as part of your earthwork. Sometimes we have processed in-place materials. Lime-treated subgrade is an example, where we're actually stabilizing the native materials. So that does count in the earthwork. So when you're working with existing materials, for example, in a lime-treated subgrade, you want to count the subgrade above that line. When you're working with imported materials, you want to count the line below that line. And I've seen mistakes on earthwork models happen in both directions, where someone just looked at the structural section and made an assumption about what needed to be included in earthwork, and it wasn't correct. So keep an eye on that when you're building your model with respect to what actually defines the typical section. Another thing that is often missed is on some projects, you have significant removals of the native or of pavements or foundations. For example, on our S1 project, we have an old building site on the project. So we're going to remove the foundations from that building, and obviously the survey went to the top of that concrete. We're going to have to manually adjust out the foundations or the slabs of the building when we build a new existing ground line. So that I've seen it happen before. You got 3 or 4 inches of existing asphalt. You're going to put embankment on it. You're really good about surveying it correctly. You're really good about calling out removals during your demolition quantities. But someone forgets to, we got to lower our ground line 4 inches to reflect the fact that we've removed that quantity of asphalt from the ground, and that's got to become our new existing ground line. So keep an eye on any removals like that. There's another thing. Once you've done those adjustments, typical section adjustments and earthwork adjustments for paving or slabs or anything like that, you can calculate earthwork from that, but that's what we call raw earthwork. There's a couple of other adjustments you can apply that kind of refine that number. When you have the green areas, or what we call ground compaction, when you have an embankment placed on native soil, the surveyor's out there and they're just sticking a rod on the dirt, and sometimes that dirt can be fairly loose, and it's standard practice to scarify that soil, moisture condition it, and compact it before you put the embankment on top of that. And in the process of doing either clear and grub or scarify, moisture, and compact, you actually tamp down, if you will, that native material, and your starting point for embankment then becomes at a lower elevation. And that's a factor we call ground compaction. And some smaller projects, it's not very significant, but if you have a project with a large surface area of embankment and a comparatively shallow depth of embankment, it can be a very significant number in your earthwork number. So one of the things to remember about ground compaction is, if you want it to be as accurate as possible, you want to get a recommendation from your geotechnical engineer as to what that ground compaction factor could be. So you don't only have to think about this when you're setting your model up, you've got to be thinking about this way back when you're scoping the project out with the geotech to make sure that he knows that that's something you're going to ask him of. And I'll tell you, they don't like to give you this because it's pretty hard to make a reasonable assumption on that, but hold their feet to the fire and make them, as the soils experts, make a recommendation to that and include that in your model. We've done the adjustment for ground compaction several different ways. We can run calculations on earthwork and then manually adjust out the area times depth of ground compaction, or you can actually lower the surface in the areas where you anticipate ground compaction by the depth. And usually it's at maybe 5/100ths of a foot, 1/10 of a foot, at the most 15/100ths of a foot for ground compaction. But that's one component of what we call adjusted earthwork volumes. Another component is the dreaded shrink swell. And when you take a native material, the blue areas, and excavate it out, let's say it's 100 cubic yards, and then the contractor places it in embankment and compacts it and rolls it, if that native soil in its in situ condition is comparatively lightly consolidated, in the embankment condition, it's actually going to take up less volume in the fill than it would if you didn't account for this. So that's the area that Joe's pointing to there. If it's a heavily consolidated material, it's pretty rare, but sometimes the material actually swells in the embankment condition. And these shrink swell factors can also be fairly significant, up to 5 and sometimes in extreme cases 10%. So they do have an effect on your volume. So these are applied inside Civil 3D. And again, just like with the ground compaction, you need to be proactive and requiring that your geotech consultant give you an estimate of shrink swell factors in his geotech report. And they like doing that even less than they like doing ground compaction, because it's shrink swell is kind of black magic and a lot of potential for error. But again, they're the experts. Put their feet to the fire and make sure you get that number from them if you have a significant quantity of embankment and you think that the shrink swell might be significant. So once we've applied the ground compaction and the shrink swell and run Civil 3D, those are what we call adjusted earthwork numbers. And those are generally what, and a lot of our projects in the airport group, we're forced to use unit price, and contractors, we have to estimate earthwork. The FAA requires that we use average end area. And so we have a bid item in our plans for earthwork volume, cut and fill, and we often get into arguments with contractors about those items because they come up with slightly different numbers than we do. And so having a good process of building these models and making sure you're taking into account all the factors we've talked about puts you in a lot better position for defending your earthwork numbers if you have to do that with a contractor. So, Joe?
All right, I am going to show you guys just a couple examples of where we had to use different styles of, or different methods to get our cut fill numbers in CAD. And this part will be fairly brief just so that I can get Ken's second portion in, and then we'll come back to it and show it a little more in depth as time allows.
Yeah, Joe, I think we have plenty of time, so don't cut it too short.
Okay. So, to start off, we have the quality control set where Ken likes, the Dibble set where we like to have the sections along with the different views. To get this, we actually create two different surfaces, or many different surfaces, and this is just one method. You can create a subgrade surface of each of your different pavement sections, existing subgrade at the or at the proposed subgrade as well. Let me go ahead and show you some of these sections. What we end up getting is something like this, that it has the cut and fill of each of those sections. So we start off with a simple, this file is the earthwork practice, if you guys want to follow along. It's nothing complicated. I created a very, very rough, as you can tell, very rough surface, existing surface. And if you guys have any questions, please ask. I can't follow the text messages as well as trying to show. Anyways, I've given you a proposed surface and an existing subgrade. One of the ways to do this is by just boundary control. So we could then create a second surface. So ignore this one. This was to create that weird little bump there. We have our existing surface, our proposed surface. So what we would do is we would create a second surface, and let's just say we call this our subgrade, and we'll make it the proposed. I'm not going to be going into naming. That's a whole different thing. This is just going to be showing you how to add it as a secondary surface. So then we paste our surface and we put our proposed. After we paste it, we can then drop it to whatever using the raise and lower surface, we can drop it to the amount that we need to. For example, let's say the subgrade is 22 inches deep. So there we go. Now we have.
So that adjusts for the paving section, Joe?
Correct. As of right now, it's going to show over here. It's going to show this entire surface being 22 inches below, but we don't want the entire surface. Let me run a quick profile here. proposed, and then the subgrade I'll make it superimposed just so we can tell the difference. Alright, so you see how it then comes down. On a bigger project, we don't want that to happen because this isn't actually being removed. We're just going to actually cut that out. So what we could do is create a boundary of just this area, and we'll put that on the correct layer. C10 boundary. Oh. 1 second, sorry, put it on the wrong layer. Alright, so then we put that on the boundary, and we go to our proposed subgrade, add a boundary. There are a couple methods to use outer, hide, and show. I might give you guys a quick glimpse into that. For now, I'm just going to use outer, and I'm going to make it non-destructive because I'm slightly inside. The more accurate you want it, the more you'll have to play with these lines and get them closer to the actual feature lines. For this demonstration, I'm just doing it up to there. So then that will cut our line nice and straight against just the pavement. Now we say we have this connector taxiway that's bringing us into this apron. We could do the same thing, and once again, if you want this to be very accurate, I would suggest getting really close to these lines. You can't overlap boundaries very well before CAD starts getting really angry at you, so I would suggest maybe offsetting it a foot or 0.1 feet. Just play with it. It'll give you errors if you can't do it, if it's too close. So we'll call this one, we'll change the name of this subsurface to our apron. Hit OK. So now we know that that's our 22-inch apron section. For example, let's say this here. Let's put this on the boundary. We'll say this area here is just our taxiway or pavement. Doesn't matter. We'll create another surface. I can't remember what I called it. Subbed. And then we'll say taxi. Proposed taxi. Sure. Okay. Then for that one, we paste our surface again, our proposed. We can do this a little easier when you're using corridors. There are some odd shapes with our projects that we can't use corridors. For example, this project here was partly made with a corridor. We were able to use a corridor here, but I don't know if you can tell, but over here, all this pavement is completely different. So a corridor would not have been the way to go. We probably could have made it work, but it just would have been way too difficult to model all this turns over here. So we did kind of a halfway corridor / 3D feature line method over here. And I'll get back to that in terms of the boundaries to help with that one. So, sorry, I got a little distracted there. Back to this one. We're going to make that. We're going to drop that taxiway, raise lower. We're going to drop it, we'll say only 15 inches. So, as you can tell, there's a whole bunch of extra contours now that we haven't added our boundary yet. We got to add our boundary. Add. You can name it. Like I said, I'm not going to do that for now. I'm just going to use outer and non-destructive. We have that one. So if I were to run a cross section going this way, we have existing. We want to show our subs and we want to show our proposed. So let's go ahead and show this as superimposed, superimposed, and 10 to 1.
Vertical exaggeration?
Yes, correct.
Yeah.
Oh, I didn't make the existing. Sorry about that. All right, so there we go. So now we have that little taxiway at 10 inches, or whatever I said, 12 inches. And then we have the bigger apron at 22 inches, I think I said. So now we can then add another surface, which there are plenty of ways to do this. I'm just showing you one way. We can add a second surface that basically is all of our subgrades combined. Proposed subgrades combined. We'll go ahead and paste our surfaces. Usually I like to start from the bigger section because it leads to less errors, but doesn't always work. So I will put the proposed first because the infield is technically still there, but it's just not going to be used as a cut fill. Well, it is going to be used, but it won't be adjusted. So proposed, and then we paste again the apron, and then we paste again the taxiway. So just to show roughly what we've done, let's go ahead and turn off all the other contours and just leave that one with the contours on. So kill the contours for there. Okay. And then let me turn those proposed combined one back on. There we go. So now we can see that there's a little bit of jump here. For this demonstration, I'm not going to really go over that. It'll have to be the next one. Or you can come ask me. I'm always available usually.
So you'd normally adjust that to model the change in the paving section,
correct,
transitioning back to native or whatever.
Yeah. I wouldn't leave it as high up either. Because when we show the cross-section here, you'll see what I mean by it. I wouldn't leave it. We want to show the combined as superimposed. Okay, so we're just going to show the proposed, the combined. We're not going to show any of these other ones, and the existing, 10 to 1. So this is that point that I was telling you about. I would probably adjust it later on and get rid of it, but for this demonstration, I'm not going to do that. So then, you can see here, it goes up to the finish grade line, and it looks good. So after we have the subgrade of that, we then can do our under Analyze Volumes Dashboard. This is where I like to do it. You don't have to actually do it from here. You can just create them here. Create under Create Surface. I think you can do a volume. I personally like to use the Volume Dashboard just because then it puts everything in order here, and it gives you all these populated for you. So for now, we're going to assume that there is no pavement that we're removing. If you were adding pavement to be removed, you would do the same thing. You'd model out your, say this here was a taxiway. You'd model out the subgrade accordingly. So just pretend it looks like that. So you would model this out, and then this line would then come down and trim out this inner portion. But for now, I'm going to pretend like there's no pavement whatsoever. And we are going to, right here, this little button, will add a 10 volume surface. So this is basically how you find both the grid and the 10 volume surface, both the same, sorry, not both the same, but they're both the same process in how you get the volumes for them. Just, we're going to go ahead and call this one the 10. So the 10 volume. Base surface, you pick your subgrade. Here you would pick your existing subgrade combined if I created one, which I didn't, but I'm going to use just existing. And then here you would use your proposed subgrade combined. This is where Ken was talking about the cut and fill factors. Ken, do you want to give a quick rundown on that again? Just very brief.
Yeah, so if you're dealing with shrink or swell, for the cut factors, you can make adjustments to those as a fraction of 1 to reflect the fact that once you remove materials and cut and put them back into fill, they're going to take a larger volume. So that's where you insert your shrink and swell factors from your geotech report.
Okay. So then you hit OK, and you have this beautiful thing here. Let's go ahead and change this to our elevations. That's basically how you do get your exhibits started for the pictures. On here you have this button here that'll give you reports. It's generate cut and fill report. So this, I'm not sure if anyone wants to chime in. I usually have to hit, oh, sorry, this is just me setting up windows. So I usually get another one.
Oh dear.
Yeah, sorry, hold on one second. There it is. I usually get another pop-up. I hit OK and just let it go. So this is how we like to save ours in Airport in the examples. Sorry, one second. So here we have our 3 different types of reports. We have the grid one, which looks almost the same, and we have the tin one, which is, they're both pretty much the same thing. After you print it out, it looks like that. Just keep in mind, if you do have a second surface created for volumes, it'll put them both in that single document. So it would show second surface right here. So I mean, if you just want to do it all in one report, that's fine. If you're trying to be more organized about it and show the different ones, you have to uncheck each one accordingly. So like you would get rid of that one and just print the second surface report. So that's the quick and dirty way to do those reports. After that, we go ahead and do our sections. So, or sample lines. Ken, did you want to talk a little bit about the sample lines and the placement?
Yeah, and I think the first 2 areas are just methods where Civil 3D can compare vertical surfaces and generate the volume between them. This is, when we're working with cross-sections, it's the more traditional method, and the value of using the cross-section method is it's much easier to check the work that Civil 3D is doing. And, you know, when we talk about the quality control process, a lot of times what we've run into is we kind of trust the black box, and with some of these other methods, that's what we have. We have a black box. But when you're doing cross sections, you can actually look at the sections and see if they make any sense. And so there's a heavy bias on my side, even if you're not going to include this information in your plans or your reports, to at least cut cross sections and look at them and compare them in your design, make sure they all make sense. So as far as the logic of cutting section, you know, the first approach is let's do them every 100 feet or let's do them every 50 feet. But the refinements to that is when you're using average end area, the way the average end area system works, if you're not familiar, is you'll have 2 adjacent cross sections, and the computer will calculate the area in one section of cut or fill or both, and the area in the other section, and it will average those by 2 and multiply by the distance. So if you're not careful in how you cut your cross sections, you can actually have an inaccurate transition from one to another. So Joe, go down to the taxiway area and we'll talk about that a little bit in terms of how you can. So you obviously need a section at the very beginning of the project right there, and then in order to capture the transition in the slopes there, you'll want another section right at the toe of the slope before you go into the apron, and then another section at the top of the slope where you go into the apron. And so you're looking at your horizontal design and plan, and you're making sure your cross sections are picking up transitions in plan from one area to another, and that will improve the accuracy of the average end area method. If you just blindly go in and put 100-foot sections or 50-foot sections without this level of refinement, you'll have some level of inaccuracy in your earthwork sections. And it's usually not huge, But when you're sitting across the table arguing with a contractor and you haven't followed best practices in terms of how you generate your sections, sometimes it makes you look less than stellar. So.
All right, and so on here we probably would put one here as well, and here. So this would be if there was a sidewalk and a building here, we'd want to capture both those areas as well because of the sidewalk and the building.
Right.
So we'll just pretend this is less or more than 100. I don't know if it is or not. So then we'll probably throw one there, and there, here, and down at the bottom.
Yeah, and then you could add intermediate as necessary, usually on even stations, so that you have a good reporting system in your sections in your reports.
All right, and so to do that, you need your alignment up. I don't know if you guys saw me do that, but I created an alignment just to get us started here. You'll use the sample lines. You'll click your alignment. You'll get this pop up here. Now you could create all this stuff and change all the names according to Dibble's sections and whatnot, but that's a different topic. I'm not going to go over that. Here you would just do your proposed. You want to see your proposed. You want to see your combined sub one, and we can change that to proposed as well. So you'd have your subsurfaces checked, your proposed, and your existing surfaces checked. Okay. So I'm just going to manually add them, but you could do all those other tools that John had discussed in the previous training. For now, I'm not going to do that. Just going to click there, click there, there, and then I will adjust the widths manually. All right, so that should be good enough for now. You would go on and add it at each one of those. I'm not going to do that for time's sake. So then you could adjust it to be here. You want to make sure you capture both proposed and existing. Go there, 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 there. Is there any other questions at the time while I'm doing this easier stuff?
Pretty quiet bunch, Joe.
Yeah. All right. So I'm going to go ahead and get rid of these bold lines. Okay. Okay, sorry about that. Let's go ahead and get rid of that. Oh, didn't want to get rid of those. That's fine. You don't need to worry about that. So then, under section views, we create multiple views. Now, depending if you're going to make this for just a check set or if you're actually adding sections to your plans, I would definitely consider having different drawings or a different drawing for these, or just preparing them so that if you do have them in a plan sheet, you can move them easily and you're not tied down to it. So what I did was I did section views, and it brings up this. This will give you a whole bunch of the different options. I'm going to leave this at 1:1. I think we have a different section view that is like 5:1 or something. But for now, I'm just going to use the default Dibble one. We're going to go draft. I usually do this one. There's a different setting. Not sure if anyone could chime in on this one. I can't remember what exactly this one does, but I don't think it's anything important. Create section views. So all that stuff was good. We're going to go ahead and change this. Oh, we're going to leave that one as proposed, and then we're just going to create section views. I like to keep it nice and organized, but for this example, we're just going to throw them off to the side here. So we got then our section views, which they all look pretty good. Pretty good. Pretty good. Now, when we're creating sheets from these, you like to put incremental going up?
Yeah, the standard practice historically has been you start at the bottom and you go up station, so you're kind of as if you're standing on the roadway or taxi or whatever and looking forward, so the higher stations are at the top and the center lines are lined up. So if you're comparing your plan view to your cross sections, you can kind of visualize how these sections march forward along your stationing. So you start low at the stations and move forward. And just to comment on, Joe mentioned whether or not you're putting cross sections on the plans. Different clients have different requirements. Different consulting firms and practices have different standard practices. But if we have significant quantities of earthwork and we are measuring earthwork on a unit price in the project, we like to put earthwork quantities in the plans. And what that does, it establishes a basis for the contractor to verify our numbers against theirs, because they can see what our numbers are based on. The other good thing about putting earthwork sections on the plans, it's amazing how it inspires a sense of accuracy on your earthwork sections when you know they're going on a set of plans that's going to be sealed. So it kind of takes the sloppiness factor out of cutting earthwork sections and saying good enough, because you really have to check them and refine them if they're going into your final product that goes to the client, to contractors.
All right, so then after you do this, we've organized them and put them where we need. We go to, under Analyze, you go to Volume Report, or excuse me, you do Compute Materials first. Hit OK. What this is asking is what's at the bottom. So we would do our existing. If we had a subgrade created for the existing, we would do existing subgrade combined, but we don't. So we'll do the proposed subgrade for the datum. And then corridor shapes, John, can you give us a quick rundown of what those would be? No.
No, John?
No,
Well,
John.
no, I'm here. Sorry, I was working at the same time. So you're wanting to know, I guess, what corridor shapes we use besides what's already what you're showing there?
Yeah, and what would these be considered? These are just...
Yeah, the corridor shapes I actually never use at all. So all I use is the EG and the datum. That's
okay.
That's all we use for our earthwork. So
Okay.
everything you've got there, it's all good by us.
Okay. So this is going to be the average end, what we're using. We have never really used these. I'm not sure if Ken has anything he wants to say about those two, but average end.
Screen is too small for me to see what they even are, Joe.
Composite volume and prismoidal?
Yeah, I think because of our bias to the ease of checking, I think the average end area is about all we've ever used.
Yeah. All right, so then you just hit OK. Hit OK. So what then that does is creates your cut fill sections. This is not plan ready, but they are there. John showed us last week how to change these, so I'm not going to go too in depth on that. You can change the style to show that differently. After you've done that, you can then do your volume report. You pick your alignment, your sample group, which we only have one in this drawing, so it doesn't matter. Your material list is the cuts and fills. And you just hit OK. Oh, this is the one that gives the pop-up. So this, I know it sounds dangerous. Go ahead and hit yes. And that'll give you this volume report. You can then print it out and save it as an individual PDF, and that is here. And that looks just like that. So we're going to go ahead and I guess conclude the CAD portion of it. It's nothing too complicated. It's mainly the volume dashboard, and you just follow it there. Or you can do it by creating a surface here. Is there any questions on that? All right. I am going to move on to... I might just show you guys one more thing, actually, before I move on. So, boundaries. This drawing here has quite a bit of boundaries. I want to show you the differences between the outer and inner. Let me just turn the color on a little bit brighter so you guys can see them. Second. Now this is a little off topic, but I figure it's a good enough time to do it since we have a little bit of extra time. Got your boundary here. You have your other boundaries. Oh, sorry. This was the one I wanted to go to. All right, so we have this building in the middle of our project that is not going to be considered part of the cut and fill numbers. So an easy way to get rid of the boundary is to do a hide boundary and a show boundary. So you would have your existing surface, or any kind of surface. You would then create your outermost boundary to hide it. Then you have your, I guess the best way to show you would be to actually do it. So let me just go ahead and create the boundary for the existing. Do a new proposal.
So if anybody's wondering, this is the North Concourse at Terminal 3 at Sky Harbor. So we did a project to remove and replace all of the pavement and regrade the apron, and the concourse is in the middle, so obviously it's staying, and so no earthwork in the building.
All right, so let's see if this is the one that contains it. Okay, this has a hide show boundary. Basically, what it's doing is it's trimming out the area you don't want to show. Sorry about that. I kind of don't know where to start. All right, so let's go ahead and just copy this existing surface. Oh man. Sorry, I'm just thinking of the best approach on this part. This is not working how I was hoping. Create a surface. All right. Let's just call this test. Okay. Let's paste our existing. There's our existing. So, as you can see, they didn't survey the building already, but I'm just going to pretend we don't want this area here in this corner. So we would hide our we would add a boundary, call it hide. We change it to a hide. Hit OK. Click on this, and then our surface goes away. But then we want to show. You could do it so that it's just a show hide, but I'm going to show you the hide show hide. And it gets a little complicated because I don't know why it needs to be this way, but it does. So we go to boundaries, add, show, and then we hit here. So sometimes you'll have a surface that comes out here and it's tinning across from these two. So that's why you would show just whatever's inside of that. So my boundary would realistically follow basically this pavement edge. So then I would click that, and if I was just realistically just trying to show that boundary, I would go there. And then I can do the hide one more time. Call it hide 2. Hide. Now you got to make sure you use a non-destructive boundary for this one. Otherwise it won't work. Click that. And there you go. Now that's been chopped out from that boundary. So that's just a quick little example of how to use the hide show.
So that would force it to not tin through the building if you follow
if you had a building there. Correct. Yeah. All right. I think that's all I really wanted to show, Ken. We'll skip over to the next part, the last part.
Okay. Yeah, the last part is basically how do you accurately check all of this good work that our designers and project engineers have done in generating earthwork. And I'll point out that some of our best practices are based on our worst mistakes. And you've probably heard me talk about some quantity busts we had at Gateway at an airport as an airport practice, and one of them was an earthwork quantity bust. And we had a taxiway project where, for whatever reason, the model didn't completely and accurately reflect the final design. And it was basically a $90,000 differential versus what was in the plans versus the contractor's actual cost. So because of that, we went through and looked at our processes and said, what do we got to do to make sure that never happens again? And that was the genesis of this earthwork quantity calculation checking recommended practice that you all have been provided access to. It's a 9-step process. It seems really complicated, but it's not. On that particular project, our designer did generate cross-sections. The project engineer and the project manager, myself, looked at them. They looked okay, but we didn't do an in-depth enough check to make sure they reflected the actual final conditions of the design. So this is really a pretty straightforward 4-step process. And Joe, if you can bring some cross-sections up, that would be good. There you go. Just like a earthwork cross-section.
Okay.
So the key to this checking process is, like I said before, you can't trust the black box. I mean, we have excellent tools to do calculations for us. And if you ever really want to be astounded, I'll tell you how we used to do earthwork back when I first started at Dibble. But we have excellent tools that do a lot of the mechanical work for us. But we can't just kind of trust that everything's right. We've got to be able to physically check it. So open up the lid of the black box, look inside, look at all the bits and parts, and make sure they're put together correctly. So the first step is to sit down with your cross-sections and your final design, whether it's a roadway alignment, it's a taxiway alignment, it's a site grading plan, and pick some spots on your design plan for elevations, and then go to your cross-section at a similar place and make sure the finish grade in the cross-section matches the finish grade on your design. And that's a very simple check, but that's exactly what busted is on the project I was telling you about. We made a final last-minute change, and it didn't get reflected in the model, and so even though the sections looked right, they weren't actually at the right elevation. So that's the first check. Look at your slopes and make sure, sometimes we have our typical sections, make sure that the slopes are falling within your typical sections control criteria and the widths and offsets are correct based on your design. And then the next thing you want to do is, going back to what we said earlier about best practices, make sure your subgrade line is correctly modeling the subtraction for your paving section, so that you're all of these checks should be done by someone other than the project engineer or designer or EIT, whoever generated the earthwork. Someone else should be doing those checks. So check your subtraction from finished grade to subgrade to make sure it matches your final typical sections and accurately projects the width and the depth of those sections. So the other thing we want to do with these sections, and Joe, you can pull up the earthwork quantity summary next to the sections. Yeah, no, the average end area one. So we should have a printout with average end areas. Okay, so we have this volume report, and we have the cross sections, and we can put those side by side. Pull up the other. There we go. So, and this is the reason why we kind of like to use average end area, because it is so easy to check. Maybe not easy, but it's so easy to reproduce what Civil 3D or your computer is doing for you. So you have your sections on one side, and you have your volume report on the other side, and you can actually, we have our designers provide us with CAD files, and you can actually do spot checks of the areas within certain cross sections and compare them to what the volume report is spitting out, so that you're kind of checking inside that black box to make sure that the final cross sections that you're going to use as a basis of your design and potentially even include in your plans match the volume report that Civil 3D is using to generate your areas. And these are raw, unadjusted quantities, so keep that in mind. But you can actually run a polyline or check the area, and obviously sometimes you have to adjust for the vertical exaggeration. That gets a little complicated. And then go over to that section and make sure that the numbers are lining up. So it's a really good way, even if it's a little tedious, to make sure that your cross sections and your earthwork reports are matching up. And then the final check that you want to do is, if you have included those adjustments from raw to adjusted earthwork, make sure they're inputted correctly into the model. Ground compaction, If that is in place, shrink and swill, if that's in place, do a verification that those have been reflected in the earthwork volume report and the calculation. So going through this simple 4-step process has saved us on a number of projects where we had issues where the work was done well, but it wasn't one-to-one matching the final design, and we were able to catch some significant issues with quantities on earthwork and make sure that they are defensible and something that we're happy to sit across a table with a contractor and argue his method versus our method, because not only is it based on sound best practices, but we have checked it to the point where we're comfortable that it matches what's in the plans and is a defensible number. So that's very important, and hopefully you can take that away as, we just can't trust the black box. We've got to make sure that the numbers we're using are matching our actual final design. That's all I had.
All right, and I think that's all I have, and it also makes a pretty picture for your reports. So
yeah, and I'll just mention that one last thing. I mean, in terms of reproducibility and checkability, we like to not only include the cross sections in our plans, but we also like to include those cross-section reports and these pretty pictures in our engineers' reports, so that if anybody down the road wants to figure out how we got to our numbers, they can pull up our design report and say, yes, I see how you got those. Here's the cross-sections, here's our earthwork calculations, and here's our volumes, stating all of the factors we used for adjustment or whatever. So that's a big part of a quality process, is make sure that your work is documented so it can be verified at some point down the road. Any questions? What?
Nope, I think they said thank you, Lurid. So I guess there's no questions. Rebecca, you wanna final words? Nope, she's not there. All right, I guess that's it.
Thanks everyone for listening to us. Some of this is pretty basic, but it's always good to be reminded of what's good practice for making sure we're able to defend our numbers.
Right, and don't forget to fill out the forms that Rebecca likes, the sign-in sheet and all that. So,
Thanks, Joe. Thanks, Ken.
You bet.
Well done, guys. Thank you.
Thanks, Ken and Joe.
You betcha.